So one other property that we need to talk about is electron affinity, and this relates to the next lab experiment you guys are going to be doing. Electron affinity is the opposite of ionization energy. It's the energy change associated when an electron is added to an atom instead of when an electron is removed. So if I'm going to add an electron to an atom, in this case, I have a free electron and I have my atom. It's got some quantity of positive charge. It has some electrons already in it. We're talking about taking this electron and putting it in to the valence level, wherever that valence level is for the atom. All right, so the same factors we talked about are going to be determining which elements have higher electron affinities. The word affinity means attraction. So this basically is just how much of this does an atom attract a new electron. Right, so when I have an element, if it adds a new electron, it will now become negative, and it will make what's called an anion. So all the factors we talked about before are still in play. We have to consider shielding. We have to consider how many protons there are. Right? The less shielding there is, the more protons there are, the more it will attract a new electron in. Also, we have to consider the noble gas. If an element makes a noble gas configuration exactly, or breaks a noble gas configuration that was exactly a noble gas configuration by adding that new electron, that's going to have a big impact on the energy associated with that. And we also will see here in a minute how having an exactly half-filled or an exactly full subshell is also a factor. So let's look at some of these examples. What do we notice for all of these examples? That the noble gases have very low electron affinities. And in fact, they're showing them negative on this chart because they're so low. So the noble gases do not have an attraction to new electrons because they already have a noble gas configuration. They already have a stable arrangement of their electrons. They're not going to bring more electrons in. If argon were to bring another electron in, where would it go? Yeah, it would go into the fourth energy level. Argon's third energy level is full. So that's one of the reasons why the noble gases are so stable. They have a full energy level. They don't want to bring new electrons in because they have to go into a whole other level that's experiencing all that shielding. Right? So the noble gases don't have high electron affinities. What elements have high electron affinities are the halogens, the ones right next to the noble gases. And those are high because if they pick up an electron, they will make the exact same number of electrons as a noble gas. We can't say the same for the rest of these. All right, so for these other elements, all the other ones I boxed there in red, those elements will neither make the same number of electrons as a noble gas by adding electron, nor will they break up the same number of electrons as a noble gas by adding an electron. So we cannot use the noble gas argument there. It only works as an argument when the number of electrons is either exactly the same as a noble gas or will become exactly the same as a noble gas by adding an electron. So for those ones, we have to invoke the other argument. Numbers of protons, degree of shielding, and sometimes having an exactly full or half-full subshell. So let's see the chart here that relates electron affinities, similar to the ionization energy ones. You can see in a given row, they go up because the halogens have the highest electron affinities because they can make the same number of electrons as a noble gas by picking up an electron. And the noble gases are at the bottom because they have very low attraction. Right? So that noble gas configuration rule is the most powerful rule when you can use it. Otherwise, we can say, as we go across on the periodic table, we're still going up, and that is because as we go across, we're increasing the number of protons. We're not really changing the shielding too much, but elements on the right-hand side have more protons, so they attract a new electron better. They have a greater attraction or affinity, a greater electron affinity. As we go down the periodic table, there's not too much of a trend here to really see, but as we go down the periodic table, generally on average, the electron affinities go down. Okay, so the reason for that is, and you can see the numbers here, they're not completely following the trend. I'm not going to hold you responsible for the exceptions, but as you go down the periodic table, you are increasing the protons, but since that's not as big a factor as the shielding, increasing the shielding is the main factor you would invoke there to explain that. So if you have more shielding, adding a new electron, it's not going to be as attracted because of all the shielding repelling it, right? So we add more repulsion for a new electron. So we have a lower affinity for that electron, or a lower electron affinity. We also have some of the half-filled, exactly filled subshell trends here. So since these are going up and down, it's not a clear trend straight up or straight down. We can explain that as well, right? So elements that have one valence electron in their S subshell, so these are the group 1A elements, they have a slightly higher electron affinity than you would expect, because if they attract one new electron in, it will completely fill that subshell. Elements in group 2A, so this is a slight factor. It's nowhere near as powerful as the noble gas factor, but a slightly greater electron affinity than expected. And these have a slightly lower electron affinity than expected. Because to attract a new electron in, it's not going to really make it very stable. It already has a relatively stable arrangement with its completely filled subshell. Attracting a new electron in doesn't really help the atom out in any way. It helps the electron that it attracted, because the electron gets to feel an attraction now to that nucleus of that atom that it went into. But from the atom's point of view, it doesn't really attract that electron. So the electron affinity is not going to be as high as you would normally expect. And the same thing if we're one away from having an exactly half-filled subshell, that P subshell, if it's 2 out of 6, if it's not exactly half-filled, that will have a slightly higher electron affinity than you would expect, because by adding it, it helps to stabilize that subshell. And if I already have an exactly half-filled subshell, it's going to have a lower ability to attract a new electron than you might expect, because it's not going to want to pull another one in and break up that exactly half-filled status and make 4 out of 6, which is not exactly half. Any questions about those? And so there are 4 factors that you might need to use to explain these on the test. The factors are shielding. Well, actually, let me list the factors in order. The most powerful factor that you're going to use is the noble gas configuration. But remember, you can only use it if the element you're talking about either makes or breaks the exact same number of electrons as the noble gas. The second factor is the shielding. So if both of your elements have the same noble gas configuration argument, that's not going to distinguish between them. So then you would go to see which one has more shielding. After that, you would go to look to the number of protons. And this is kind of on the same level as the exactly half-full subshell argument. So those two, at that point, it gets a little complicated to try to figure out which has more proton, or which is going to have a higher ionization energy or electron affinity. But those are the arguments that you would make in the explanation part of your answer on an exam. So if we're looking at aluminum versus silicon, first thing we look for is the noble gas. So if I'm looking at aluminum and silicon on the periodic table, can I make an argument about their electron affinities based on a noble gas configuration? No. It's not correct to say silicon has a higher electron affinity than aluminum because silicon's closer to a noble gas, and it will make it closer to a noble gas configuration if it picks up an electron. That's not a factor there. You can't make that argument. Because it's not going to make a noble gas configuration for either of those. Picking up one electron, the noble gas configuration is not a factor. So we can't use that argument. So we have to go to the next argument. Between aluminum versus silicon, is there a significant difference in the shielding? No. They both have their valence electrons in the third energy level. So they both have 2 levels of shielding, doing the majority of the shielding, and then they have the third level where that new electron is going to come in. Right? So also, when you're talking about electron affinity, you're not really thinking about the electrons that are already there as much as you're thinking about what it's going to look like when a new electron comes in, right? Because it's going to have to pick up this electron and put it somewhere. So if I'm thinking about the aluminum has a 3s2, 3p1. The silicon has a 3s2, 3p2. So I'm thinking about making this, I'm going to put my electron in here, or I'm going to put my electron in here. Either way, it's basically the same amount of shielding, so that's not a factor. It's not going to help us distinguish. So then we've got to look to these 2 factors. And actually, probably I want to switch these. Switch those up if you can. If this one is applicable, it should take precedence over the number of protons. So we want to look for that first. Sometimes it might not be a factor, but we want to look for it. So if I add a new electron to the aluminum, is that going to make or break an exactly full or exactly half full subshell? No, it's not going to do anything for the aluminum. Will it make or break an exactly full or half full subshell for silicon? Yes. So if the silicon picks that electron up, it'll go from 3s2, 3p2 to 3s2, 3p3. And this is exactly half full. So does that mean the aluminum or the silicon is going to have a slightly higher attraction for that electron than expected, or a slightly lower attraction? Slightly higher, right? Putting that electron in makes it more stable and makes the subshell half full, so that will have a slightly higher attraction than normal. So that is the deciding factor. This should have a slightly higher electron affinity than aluminum. Well, also the other factor suggests the same thing. Silicon has 14 protons, aluminum has 13. So the extra positive charge also helps to attract a new electron in there. So there's really 2 reasons that you can invoke to explain that.